Friends, today in concern with relativity, we will discuss about special theory of relativity and Lorentz transformation equations. See, in special theory of relativity, there are two important postulates, and this special theory of relativity is based on these two postulates. First is the laws of physics are the same in all inertial systems. There is no preferred inertial system. Means we cannot say for inertial frame of reference or non-inertial, etc. There is no preferred inertial system. And second one is the velocity of light in free space has the same value for all observers irrespective of their state of motion. Again, the velocity of light in a free space has the same value for all observers irrespective of their state of motion. We will see what these postulates states in a described manner. The first postulate brings out the fact that the universal frame of reference is not in existence. See this statement. As per the first postulate, he says that the universal frame of reference is not in existence. The first postulates we will recall our memory was that the laws of physics are the same in all frame or in all inertial frames of references. And therefore he says if the laws of physics were different for observers in a relative uniform motion with respect to one another, these differences would enable us to determine which objects are stationary in space and which objects are moving. But such a universal frame of reference is not available, and we are unable to notice such differences in physical laws. And the second postulate, it states that it follows directly from the negative results of Michelson-Morley experiment. In last lecture, we have discussed the Michelson-Morley experiment and many other experiments performed by the same purpose. See, now we will discuss about the Lorentz transformations. See, based on postulates of Einstein, the Lorentz derived transformation equations. Here we considered the two frame of references that are S and S prime. Let S prime is moving with a velocity v with respect to S. Take the axis in the two systems along the direction of motion of S prime with respect to S. Let the two remaining axes in S be parallel to the corresponding axis in S prime. Let the observer O at the origin of S and another observer O prime at the origin of S prime, another system. And these two observers are observing the same event. Let this event take place at the instant t, at the point x, y, z, as observed by O, and at the same instant time is t prime, and the points are x prime, y prime, and z prime, as observed O prime, as shown the figure plotted below. See this. These are the two systems. This is a O, this axis x, y, z. This is the one system. Another system O prime, x prime, y prime, z prime. And here the coordinates is the p, x, y, z, t. And for x, y, z, t for this frame of reference. And for this frame of reference, it is x prime, y prime, z prime, and t prime, and y prime. See now, here we have to establish the relationship between the corresponding coordinates of the two systems. The relationship between x and x prime may be assumed to be in this way: x equals to k in bracket x equals to vt, k into x equals to vt. This is the equation number 1. Where k is a constant, this constant does not depend upon x or t, but many times it depends on t, but it may be depend on t. The choice of this equation from amongst many that are possible is justified because it is a simple and linear equation. See friends, according to the first postulate of theory of the equations of physics, must have the same form in both frames of references, that are S and S prime. Therefore, taking into account the difference in the direction of the relative motion of S and S prime, we change to sign of V, and we are able to write in this way: x equals to k in bracket x prime plus v into t prime, and this will be our second equation. See here, the factor k has the same value in both systems, that is for the system S and S prime. And these things we can write y equal to y prime and z equal to z prime. We will give the equation number 2. See here, we are able to substitute these values for x prime in equation 2. From equation 1, we get x equals to k in bracket k, again in bracket x minus v2 bracket close plus v into t prime. By solving this, we will get k into k is k square, and it is multiplied by the factor x minus v2 plus this k in multiplication k v t prime, and t equal to, we can write here by kt plus 1 minus a square k v bracket close into x. See here, to find out or to evaluate the constant k, we make use of the second postulate of the theory. At the instant t equal to t prime equal to 0, the origin of the two system measure speed of light in their respective frames, they will both find velocity to be same as c. This means that the s prime equal to x equal to ct. This is nothing but the equation number 6, and in the frame s prime, the x prime equals to ct prime. We will give equation number 7. Here friends, we will substitute the quantities h prime and t prime in equation number 7 from equation 1 and equation 5. Then here we will get these factors, that is k in bracket x minus 3t equal to ckt plus 1 minus k square upon kv into cx. Solving this equation for x in here, we will get this much factor, and by simplifying this equation number 8, we will get the k equal to root of 1 minus v square upon c square. Now friends, we will insert this equation for k in equation number 1, 3, 4 and 5, and by which we will get the Lorentz transformation equations for which we are working. See here, x prime equal to x minus vt root of 1 minus v square upon c square. Here y prime equal to y and z prime equal to z, and t prime equal to t minus vt upon c square in square bracket 1 minus v square upon c square. By writing negative in place of v and interchanging the primed and unprimed quantity, we get the inverse Lorentz transformation. And this is nothing but the inverse Lorentz transformation equation, and by which we are able to get the t by solving t equal to t prime minus of dt upon c square root of 1 minus v square upon c square. Thus the measurements of the position and time are found to depend upon the frame of reference of the observer. See friends, these are nothing but the Lorentz transformation equations. In beginning, we have been discussed about the postulates about the special theory of relativity, and on that postulates how the Lorentz transformation equations can be derived for this. Though these are the steps in mathematical steps, but you have to work out it in detail by observing, and you can write all these things on a plain paper by watching the videos, by watching the online this lecture. And friends, as the situation is going on normal, and as per the government norms, you have to attend the classes by getting vaccinated. See, there is a better understanding of offline lectures. Offline lectures are already started, and therefore try to come in classes. Yes. We will meet on a next lecture next time. Thank you very much.